First speaker is Yanovich from Institute of Information Substitution Problem, and the topic is manifold estimation.
Thank you for the introduction. This is a joint work with Alexander Bernstein and Alexander Yanovich, and the topic is asymptotically optimal method for manifold learning and manifold estimation. My talk is divided into three parts. Firstly, I'll tell a bit about manifold learning, then I will present main results, and finally give some explanation for these results. Well, let's start. The dimension reduction problem is to extract low-dimensional data from high-dimensional space. And usually, in real life, high-dimensional data lies on or near some low-dimensional manifold. So, the manifold learning problem is the dimension reduction problem when we suppose that data space is some low-dimensional manifold. More formally, we study our manifolds using finite samples of points. We suppose that these points are identically distributed, independent from some continuous measure. And we suppose that there is no noise, so these points are exactly on manifold, and all our results, of course, are probabilistic because of the random nature of the sample. That is, for some events, for example, when our training points lies only on some area of the manifold, we of course would say nothing about the other part of the manifold. But the probability of such events is low, and I'll tell about it later. Well, more formally, manifold learning is to construct two mappings using the finite sample. And the first mapping is embedding, and it maps data space to some low-dimensional space. We suppose that the dimensionality of low-dimensional space is known, and this low-dimensional representation of high-dimensional points is rather good. So we could, using this low-dimensional description of high-dimensional points, reconstruct high-dimensional points. And this is the second method, called reconstruction method. And to measure quality of such pairs of mappings, we will use some functions measures the distance between initial points and composition of embedding and reconstruction mappings of these points. It is also worth noting that manifold learning solution determines database manifold, which is and we want the database manifold to be close to the unknown manifold which we want to estimate. There are some assumptions about the manifold. First is that our manifold is covered by a single coordinate chart. This means that exists some set in low-dimensional space, let's call it there, and some mapping that our manifold X is just F of the other assumption is that our mapping is well behaved. This is the conditions on the smoothness, and they are presented here. They are rather clearly. And the next assumption is that our manifold has no short circuits. Informally, it means that such cases for manifold X are prohibited. There must be some epsilon u with positive epsilon with no self-intersections. Grossman-Stiefel eigenmaps algorithm gives solution for manifold learning problem, and for this solution, data-based manifold is close to the unknown manifold, and also denote L of x is the tangent space for the manifold x, and L theta is tangent space for data-based manifold. And the GC algorithm also provides this inequality. Here is an example of numerical experiments with GC algorithm. Here we take rather popular in manifold learning example called Swiss roll. And here is the unknown manifold, example of points on it, and here is independence of log 10 in error and training size. Horizontal is training size, and vertical axis is log 10 mean error. And you may see that if the sample size is 200 points or more, the GC algorithm provides better solution than our well-known algorithms. And let's consider the next example. Here we fix training size and change our manifold in order to, for example, the first is such manifold with only one row, and we change the number of rows in order to make our unknown manifolds to be more complex. And here is also the results of this experiment, and we also may see that GC algorithm provides better solution, and for more complex manifolds, the condition about having no short circuits is not true, so all algorithms provide bad solution. It's due to the it is impossible for such complex manifolds and small training size to estimate even tangent spaces for this manifold using TCA algorithm. And the goal of our today's study is to provide theoretical analysis of GC algorithm, that is, to find rate of convergence of this algorithm and to find the symptotic expansion of this solution. And the first main result is about rate of convergence, and the following result holds true, that there exists two positive constants, depends only on the manifold but not on the point on it, such that the reconstruction error is upper bounded with the following equation, and distance between tangent spaces we use Bineka-Shih distance. is also bounded by the following equation. This result holds true with high probability, which means that the set of events IN where n is positive recurs with high probability means the following equation. For all alpha greater or equal to 1. And you may ask, so what? The main thing is that this rate of convergence coincides with the known minimax lower bound for Hausdorff distance between manifold and its estimator, provided by the following inequation. So we may say that the GSE algorithmic solution provides optimal rate of convergence for manifold learning problem.
What is the set over which you are taking the infimum? Yes, this one.
The infimum takes over the all estimates of the manifold.
Okay, so I can take any measurable function f and g.
Yes.
Okay.
To present the second result about asymptotic properties of GSE solution, I have to introduce to note some things. The first, if the manifold is covered by a single map, then exists some set in low dimensional space and mapping such that the manifold is defined by this set and mapping. And if one takes an arbitrary mapping from low dimensional space to low dimensional space, then also the following pair of open set and of the mapping also defines the same manifold. So it's just a reparametrization of the manifold, nothing more. So this pair defines the same manifold, and using only training points from high dimensional space, one cannot say which pair defines our manifold. So if our manifold learning solution, our pair, provides the low dimensional set and mapping which are close to some manifold parameterization, then the solution is rather good. Well, and the thing is that there exists some data model such that with high probability our GSE solution for manifold learning problem has the following form. The result of embedding mapping could be represented to the second order in the following way, and its Jacobian matrices also could be represented in the following way. There our O of n are uniform on our manifold X. Just note that span of Jacobian matrices are our tangent spaces for the manifold.
Sorry, but this R1 and R sub 2, how they behave, what they are?
There are explicit, these are known functions which I can write, and they are uniform on the manifold X. Well,
Could they give a more error in this estimate, because it depends on X now? Okay, but I'll ask you.
no, the error doesn't depend on X. these are some functions, and I just want to note that these are known functions that I can write, and one can't take them into account while solving manifold learning problem because of they depends on unknown manifolds, and write them while finding the solution. Well, and now I'd like to present the main idea of GC algorithm and give some notes about such parameterization of the manifold. The idea of GC algorithm is to have small reconstruction error and to use first order Taylor expansion of our mapping. Here all quantities in this equation are unknown, and in order to estimate them, one can firstly estimate Jacobian matrices as smooth bases for tangent spaces. Then, using the following equation, estimate embeddings as this is just a regression problem. And finally, to estimate reconstruction mapping result, one can also use some regression equation. The main problem is to estimate Jacobian matrices, and we want to solve this problem into two steps. Firstly, we will estimate just tangent spaces for points, and then to find in these tangent spaces some smooth bases. And the first step solution is rather simple. One may use local PCA with some parameter of the neighborhood, and it provides some estimates for tangent spaces which are rather good. And the second step is more complicated. Here we have estimates of tangent spaces, and we are looking for the small matrices x as function of x, such that they define the same tangent spaces but are smooth on x. And one can find such solutions using the following representation, just multiplying our estimates by square matrices of with size well, numerically it can be formulated as such optimization problem to find this set, minimizing the following function, which represents the nearness of our matrices. And this optimization problem is equivalent to some generalized eigenvector problem, and solving this problem, one may have a numerical solution of it. And theoretically, this solution is good enough, and to show it, one may consider some matrices of size p times q, and considering the following optimization problem, continuous optimization problem. Here, nabla is just a gradient on manifold, and the solution of this problem is the Jacobi matrices for some parameterization of our manifold under some conditions. And using this theorem, it can be shown that the following representation stands true for the matrices H of X. Through the theorem, we used results and ideas from some of Groting's articles, and the idea is the following. Firstly, we define Laplace-Beltrami operator on manifold. It's just a Laplace operator, but not in the whole real space, but just on the manifold. And from the Stokes theorem follows that some operators are formally adjoint, and the eigenvalues of sample problem convergence to the eigenvalues of the continuous optimization problem. And the eigenvalues of Laplace-Beltrami operator are rather good, so the eigenvalues of our optimization problem are good too. Finally, the following representation can be driven. As a conclusion, I'd like to say that symptotical analysis of Grossman-Stiefel eigenmaps algorithm for manifold learning problem was given, and it was shown that the rate of convergence of this algorithm is unimprovable. Thank you for your attention.
So usually the rate of convergence depends on the smoothness of the object that you are estimating. What are the smoothness assumptions that you have here for your manifold?
We assume that our manifold is rather smooth. It is twice different, and
but generally, if you assume twice differentiability, the rate of convergence is faster than the one that you have shown here.
Yeah, but you estimate the derivative. So basically.
So my question is, in the lower bound results of Genovese, Wasserman, and Kothos, the smoothness assumption is exactly the same as in your case. Yeah.
yes.
But you should show not your result, but the result the same year. That it can be. There are some bad manifolds on which you cannot get better rate. It's
Yeah, but
result of
that was exactly my
It
question.
was the question, why is this rate?
Yes,
the
the
second-
assumptions are.
And a second question. So your lower bound is for the Hausdorff distance, but your upper bound is for another distance, right?
Yes.
Is there a clear link between two distances, or?
Hausdorff distance doesn't depend on each point, but we provided the estimate for point and composition of embedding and reconstructing. So we not only provide the Hausdorff distance, but also provide for each point of x some our estimate, which is not far from the 2 point.
So you have also lower bounds for your.
the Hausdorff distance is only smaller because there is
Yeah,
point
that's
and
my
then
question.
if the Hausdorff distance is smaller and they gave an upper bound for their distance, it's also upper bound for Hausdorff distances.
Yes.
So maybe just to confirm, so you assume second smoothness of the manifold, but manifold estimation in some sense includes the estimation of the derivative because you're doing everything in the tangent space, and therefore so it's just smoothness one.
But if you assume more smoothness, you can get better, right?
Yes, probably.
But not with this procedure probably. So this doesn't exploit it.
Yes.
Oh,
Yeah, I'd like just to make a remark. You began your talk by saying, as it is well known, all signals belongs to low-dimensional manifold. I think this is very wrong. And the talk is very nice, and the result is nice. But this motivation is very wrong, and it's important to know it, because otherwise one really misses all the difficulty of machine learning. You take big signals, images, sounds, they are absolutely not in low dimensions. And when they are low dimensional structure, they are absolutely not regular. No regularity. If you take an image and you translate it, it's a two-dimensional manifold, it's a completely regular manifold. There's discontinuities in the image. If you take a texture, it's a very high-dimensional random process. So the two assumptions, I mean, again, manifolds are very useful in many frameworks and so on, in particular when there are articulation bodies, things like that, but it's important to understand that there is a limited framework, especially when you begin to put regularity conditions on the manifold, but also conditions on the dimension.
So, I think a very nice remark. So I mean, it's an ongoing project. I heard already several talks, and I asked exactly the same question. Actually, it's planned. It started already to look that your basic assumption is weaker, that the data can be approximated by a low-dimensional manifold.
Yeah, but that's
Yeah,
but the work is very nice. Okay, it's but even of course it's approximated, but data cannot be approximated. I mean, root data are not. Then you can
Yeah,
reduce.
no,
you can
this is
build environments,
simplification.
but,
Some simplification, yeah. So more remarks or comments?
One
Yeah,
more
please.
question. Do I understand correctly that the original set of data is a finite set of points in some finite dimensional real linear space? Yes, it is so.
Yes.
Yes. But when we say real dimensional linear space, we have not yet said anything about the metric accepted in that space. Which metric do you assume? I believe a usual Euclidean metric, yes?
Yes.
I believe here is the point. It is enough to take another metric, yeah? And the picture will be absolutely different. Yeah?
Absolutely. It is a finite.
Actually, the problem is to find an appropriate metric, such a metric, which would satisfy some simple subspace in another linear space. The set of points is the same, maybe a subset, but simply the metric is different. And the work is oriented on the problem how to find that new metric. I believe,
Yes.
yes, it is just this. How to change the metric so that the required desired subspace would be a linear subspace, not a manifold of some complicated shape. Yeah?
We don't
It is enough to change the metric, it will be a usual subspace. I believe so, yeah.
We just use the closeness of the points, but not the linear structure. And we use metric in low dimensional space, but it also is for finite dimensional space, and
The mapping changes the metric. Yeah.
yes, but
If you choose some metric, you actually choose a new metric. Yeah.
but the order between points to be close or to be far is invariant of this on the way you choose your metric.
I think so. This is
It's a
also
philosophical
interesting.
question. I believe.
Yeah, interesting discussion, but probably can be continued after. So if no more questions, so I suggest to send Yuri for next presentation.